Today, we're going to review for Exam 7 and Chapter 13 in your textbook on the topic of gases. I'm going to be working from the review document. I've highlighted a few of them that I want to be sure and get to. So, let's take number 1. There are two balloons, both the same size and temperature. Right? So we got balloon here and a balloon here. So their volumes are exactly the same. And their temperatures are the same. One balloon contains hydrogen and the other contains carbon dioxide. So we'll just arbitrarily say that one's hydrogen and this one is carbon dioxide. The hydrogen balloon floats and the carbon dioxide balloon sinks. All right. So what is the mathematical relationship of floating and sinking? Any object you place in a fluid, in this case, the air we breathe, if it has less density than that fluid, it will float. If it has greater density, it will sink. So if the density of the atmosphere is, say, this, then the density of the hydrogen would be less than. And the density of the CO2 would be greater than. Which balloon contains a greater number of molecules? All right. So this is a perfect example of a word problem meant to confuse. It gives you all this extra information. You only need that information and that information. And these balloons are together in the same atmosphere, so they have to be the same pressure also. And we turn to Avogadro for the answer. Whether or not it floats or sinks is immaterial to answering the question. All we need to know is that's equal, these two are equal, these two are equal, these two are equal. That means those two are equal. They have exactly the same number of molecules in either one. That's Avogadro's law. Number 2. You place 15 grams of nitrogen gas and 15 grams of hydrogen gas in a container fitted with a massless, frictionless piston. Okay. If the original volume of the container is 11.4 liters, what's the volume after the reaction has run to completion? All right. So let's say we have a vessel. It has a frictionless piston. So we need one like this. Okay. It has a piston in it. Okay. And we have 15 grams of nitrogen to begin with. So we have nitrogen gas and hydrogen gas. Okay. And if we write the equation out, it'd be like that, and it goes like this and that. Okay. So these are all gases. And we start off with 15 grams of nitrogen and 15 grams of hydrogen. Okay, we let the reaction run to completion. We assume the temperature is constant. The pressure is constant, right? Pressure is the same. temperature's constant. Let's see. Pressure, temperature, volume, and moles. So what's going to change? Well, if this is constant, and this one's constant, then during the reaction, we may get a different number of particles. If we change this one goes up, this one goes up. Or if this one goes down, this one goes down. Okay, it's direct proportion. All right, so how do we figure that out? Well, we know the initial volume, right? We know, let's see, let's put it over here. We know the initial volume is 11.4 liters. The question is, what's the final volume? Well, if we have 15 grams and 15 grams each, then we know how many moles. We can calculate how many moles of each. Because 15 grams of nitrogen, let's see, 15 grams of nitrogen, and we can say grams per mole. So we need nitrogen, which would be 28.2 grams, 0.02, okay? Would be 0.5353 moles of nitrogen. Okay. How about hydrogen? Well, hydrogen is that many grams, but we have a different conversion factor. This would be 2.02. So 15 and 2.02 is 7.4257 moles of hydrogen. Okay. If we let this reaction run to completion, which one of these reactants is limiting? Which one runs out? Well, if we have this represents 1, then this has to represent 3. 3 times that is about 1.5, right? So we've got plenty of hydrogen. That means this is limiting. And this is excess. Right? All right, so how much of the hydrogen did we use up? Well, we're going to use up all of this. Right, that's 0. And we're going to use up 3 times 0.5353. Right. So let's switch that one and multiply it. This one is 1.606 subtracted from 7.457. 4257. There we go. 5.8197 moles. Okay. So the initial moles, the original moles is just this one plus that one. Right? These two together, that's what we start with. So this is 7.9610 moles. And what we end with, that's all gone. Right? That's it. But we have this many moles of hydrogen left, but we converted this one into twice as much ammonia. Right? So ammonia is going to be 2 times 0.5353, which would be 1.0706 moles. And that's ammonia. So what we have left over is this amount plus this amount right there. And 1.0706 plus. So the final amount is 6.8903 moles. So we actually have less, right? We've decreased the number of moles. Okay, now that we know these values, we can use Avogadro's law, right? V1 over N1 equals V2 over N2. And we're going to solve for V2. So V2 equals V1 N2. That looks like nitrogen. Let's change that. N2 over N1. Okay, so that means we just need to substitute V1, 11.4. N2 is 6.8903 moles. And then N1 is 7.960 moles. Yeah. Okay. So we'll say 11.4 and 6.8903 times, and then 7.960 divide. And I get, let's see, they're rounding off to 3. That's reasonable. 3. We get 9.87 liters. Moles cancel, left us with liters. 9.87 liters is your answer. It all comes back to this relationship here. We needed to know these values in order to solve the problem, and that took some extra work. Work through the stoichiometry, like we've done before, and find out exactly how many moles we start with, how many moles we end with. Then we can use Avogadro's law. Number 7. Right. You're holding 4 balloons, each containing 6 grams of a different gas. Each one has a different gas. The balloon containing which gas is the largest? Okay, so we have 6 grams of each gas, and they're varying sizes. Let's just say we get bigger as we go down. Each one has 6 grams of gas. Okay? So what do we have to choose from? We have nitrogen, helium, krypton, and neon. Right? Those are our choices. How do we know the difference? If the masses are the same, and we have molar mass is mass per unit moles, right? That's molar mass. Then if the mass is the same, then as the moles get bigger, let's turn that around. We want to know how many moles, right? If we know how many moles of each gas relative to one another, then we can say something about the size of the balloon, because the more moles means bigger size. So let's solve this for moles. This is mass over molar mass. Okay, now we can say something. This is going to vary according to the mass is the same. So as the molecular weight gets bigger, moles get smaller, right? So the molecular weight here is going to be greater than this one. All right? We just need to figure out which one's which. So we need the molar mass of each gas. This one's 2 times 14.01, which is 28.02. Helium is 4.00. Krypton is 83.80. And neon is 20.18. 20.18. So the largest molecular weight here is krypton. The next is nitrogen. The next is neon. And the biggest one's going to be helium. All right. So to answer the question, the balloon, which is the largest, is helium. Number 8. Hydrogen peroxide decomposes to form water and oxygen gas according to the following equation. All right. Let's see. I'm going to put that equation up here. H2O2, and this is aqueous, and it yields water and hydrogen and oxygen gas. There we go. All right, what are we given? Suppose 145.9 grams of hydrogen peroxide. Grams of hydrogen peroxide. Decomposes and all the oxygen gas is collected in a balloon at 1 atmosphere and 25 degrees. So we're going to do a complete decomposition and make so many moles, right? Moles of oxygen. That's a question. At 1 atmosphere and 25 degrees. This is equal to the pressure, and this is the temperature. 25 degrees C equals temperature, but we know we're going to need Kelvin, so that's 298 K. All right, so what can we determine the volume of the balloon? Yeah. Let's see. Let's go over here. PV equals nRT. Solve for volume equals nRT over P. Do we have the information we need? R is a constant. T, we know the temperature. P, we know the pressure. We just need to find out the moles. So how do we go from there? Stoichiometry says you can't go anywhere in a balanced equation unless you have moles. Mass won't get it. So we're going to take this and convert it to moles. Grams on the bottom, moles on the top. We just need to know 2 times 1.01 and 2 times 16. Right? So that's 34.02, I think. Let's see, 32.202. Yep, grams per mole. So we need 34.02 here. And that tells us how many moles of hydrogen peroxide. 145.9 and 34.02, divide that. So this is 4.2887 moles of hydrogen peroxide. Now, what's the how are we going to get from here to there? We need a conversion factor, H2O2 and O2. The relationship is 1 to 2. Right? So I just divide by 2. And 2.1443. 1443 moles of oxygen gas. Okay, so now we have 2.1443 moles, and R is 0.08206 liter atmospheres per mole. Okay, and temperature is 298. Okay, divided by 1 atmosphere. Okay, that's the hard part. The rest is number crunching. Okay, I get 50, let's see, 3 significant figures. Yeah, that's 3. 5.24, nope, 52.4 liters. Okay. Think about what the question is. What's the volume of a balloon? How can you find the volume of a balloon? Well, there are several ways. But do you have the information? Right? And since we don't know a before condition to give us an after condition, we don't use the before-after situation. What we need is a state function, and that is the ideal gas equation. Then you say, what do I have? What information do I have? What do I need? Then you work back and find out, do I have the information? Yeah, you can find out what you need and go with it. All right, let's go to number 11. That one's getting weak. Pick up a fresh one. A gas is collected over water at a certain temperature. The total pressure is 758 torr. That's millimeters of mercury. The vapor pressure of water at this temperature is 17 torr. The partial pressure of the gas collected is. All right, sometimes drawing a picture helps. Right? If we're collecting gas from a reaction, right, we have a container here that has water in it, and we've got a device here, say a graduated cylinder, and we got bubbles coming up here. This is filled to the top with water. And then wherever it lands here, and to equalize the pressure, of course, you have to take that and drop it down until the level of water here is the same here. That way you know the pressure inside is the same as outside. Okay, so what are we given? Total pressure is 758. Right? So total equals 758 torr. All right. What's the, and you know you have a gas in here. You have pressure due to the gas and pressure due to the water vapor is equal to the total. Right? Total pressure. So what's the pressure of the water at that temperature? 17 torr. So if this is 17 torr and the total is 758 equals the pressure of the gas plus 17. So the pressure of the gas is simply 758 minus 17. So that's 1 for 741 torr. Okay. Let's see, who's next? Skip a few and go down to 18. All right. Flexible weather balloon contains helium gas at a volume of 855 liters. Initially, the balloon is at sea level, so the pressure is 1 atmosphere yields 855 liters in that balloon at 25 degrees. And the barometric pressure, well, not 1 atmosphere, actually 0.947. Okay. So the balloon then rises to an altitude of 5,500 feet where the pressure is 0.785 atmospheres and the temperature is 15 degrees. What's the change in volume of the balloon as it ascends from sea level to 5,500 feet? All right. So what type of problem is this? Is this a state function or a before and after? We have a request for we are given a volume, we want to know a final volume. We're given an initial temperature, we have a final temperature. We're given an initial pressure, given a final pressure. That's a before and after. And since we have several variables, we need to go to the combined gas law. Right? P initial, PV initial over T initial. Now, why didn't I put moles in there? Because the amount of gas in that balloon is not going to change. The moles of gas will not change. So we don't need that term. Final over final. Okay? Now, which one are we looking for? Well, look at the question. What's the change in volume? In order to find the change, we have to find what the final volume is. Then we calculate the change. So let's build our table here. What's the initial pressure? 0.947 atmospheres. Right? What's the final pressure? 0.785. Okay. How about the initial volume? 855 liters. What's the final volume? We don't know that. That's an unknown. Initial temperature is at 25. Okay. 25. We know we're going to have to convert it, so we might as well go ahead and do that. 298 K. And final is 15, right? degrees C plus 273, which should be 288. Okay, so now we have all the information we need to get a partial answer, the final volume. Then we can calculate the difference. So we're going to solve it for this term right here. There we go. So the final volume is going to be, I'm going to leave the units of measure out just to save space. Initial pressure. Initial volume. Final temperature. Initial temperature. And final pressure. 0.785. Okay, so this is the final volume. Which is 997 liters. What's the difference? The difference in volume is always final minus initial. VF minus VI. So the final is 997 minus 855. Which would be 142 liters. Positive. That means the volume increased by 142 liters. Scientific notation. 1.42 times 10 squared liters. There we go. All right, number 21. Consider the following unbalanced equation. All right. C2H5OH is ethanol, 1.55 grams of ethanol, reacts with 10 grams of oxygen. What's the total volume of gas present in liters after the reaction is complete? Assuming the reaction takes place at 1 atmosphere and 25 degrees C. All right. So the first thing we have to do is balance the equation. Okay. And they're all gas except water. Plus oxygen gas yields carbon dioxide. Okay. First thing we have to do is balance this equation. So let's use our budget method. We have carbons, hydrogens, and oxygens. That's it. So we have 2 carbons. We have 5, 6 hydrogens. We have 1, 2, 3 oxygen. On this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygen. All right, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so where do you start? Well, we're going to hold oxygen to last. That's one of our tricks because it's a single element. So I'm going to go with carbon first. Let's put a 2 here. That makes 2 carbons, right? 2 carbons, but it changes the oxygens to 5. Okay. About hydrogens. Well, we have 6 on this side. We need 6 on this side. So if I put a 3 here, that gives me 6 hydrogens, but now the oxygen changed again. 4 plus 3 is 7. All right. Now we have oxygen in 2 different places on this side. So if I put a coefficient in front of this one, it only has to account for 6 of those because I've already got 1 here. So if I put a 3 here, that's 6 plus 1 is 7. Now our equation is balanced. Next, let's go back to the question. What's the total volume of gas? What do we need to know to find the volume of gas? Well, we don't have a before and after, so we have to use our ideal gas equation. So we need PV equals nRT, right? And what do we have? We have a temperature of 25 degrees. I've got that one. That one's a constant. How about volume? That's the question, right? Pressure, 1 atmosphere. Got that. So in order to get this one, we need that one. Total moles of gas. If we start off with 1.55 grams of ethanol and 10 grams of oxygen. If you have 2 reactants and you have absolute amounts of both of them, one of them's going to run out. So we got to find the limiting reactant. So let's convert this to moles. All right, 1.55 grams. We need a conversion factor, molar mass. So what's the molar mass of ethanol? Well, let's see. It's 2 times 12.01 for carbon, 6 times 1.01 for hydrogen, and 1 times 16 for oxygen. So let's see, 24.02 and 6.06 and 16. This is 46.08 grams per mole. Divide that into 1.55 and I get 3.364 times 10 to the minus 2 moles of ethanol. That's my abbreviation for ethanol. Now we need oxygen. So how do we get oxygen? Well, let's see. We need grams on the bottom, moles on the top. 2 times 16 is 32. So 10 divided by 32 is 3.125 times 10 to the minus 1 moles of oxygen. Okay. Now, we have a couple of ways that we can solve this one. We can say, all right, if this is 1, then what's 3? 3 times this and then compare it to that. But we do need the moles of CO2 produced, right? Water's a liquid, so it doesn't count. We have to say that the water has a negligible volume. So why don't we use the procedure where we convert each one to carbon dioxide and find out which one's limiting. So this one is going to be times ethanol and CO2, and the relationship is 1 here and 2 there, right? So that's equal to, let's see, flip that one and 2 times it. 6.627 times 10 to the minus 2 moles of CO2 could be produced by that much ethanol. How about this oxygen? Well, let's see. Let's flip that one. First, let's take 3.125 times 10 to the minus 1 moles of oxygen and convert that to CO2. Oxygen and CO2. And the relationship is 3 here and 2 there. So let's see. Let's flip this one and say 2 times and 3 divide. This is 2.083 times 10 to the minus 1 moles of CO2. Okay, so we're comparing this one with this one. Which one is smaller? That one right there. This one is due to ethanol. Right, this is from ethanol. So this one is limiting. Okay, we're going to use all of that up. So there's no ethanol left. It's all gone. All right, so this number of moles of ethanol is used up. Okay, so what do we have left? Well, if this is the limiting one, then we have this much CO2, 6.627 times 10 to the minus 2 moles of CO2, and we have some oxygen left over. How much oxygen did we actually use? Well, if this, let's see, well, first of all, we produced this much CO2. No, we didn't. Excuse me. We produced this much CO2. Oh, we started off with this much oxygen, right? That much oxygen. How much of it did we use? Well, we used this ethanol converted to that oxygen. So for every one of these, we have 3 of those. So 3 times this one, right? And that's how much oxygen we used. So it's 3.364.2 3 times. So we actually used 1.009 times 10 to the minus 1 moles. That's how much we used of oxygen. How much oxygen do we start with? Well, we started with this much right here. Right? So what we have left over, we have this much CO2, plus we have oxygen, and that's due to 3.125 times 10 to the minus 1 minus what we used of it, 1.009 times 10 minus 1. Okay? So 3.125 exponent 1, change the sign, get that minus. So this is 2.116 times 10 to the minus 1 moles of oxygen remain. So this one and this one are the total moles of gas remaining after the reaction. 6.627, 6.2 change the sign, plus. So we get 2.779 times 10 to the minus 1 moles of gas. Right? That's the number of moles of gas that go right here. Okay, so now we need to solve that equation for volume. Volume equals nRT divided by P. So N is 2.779 times 10 to the minus 1. R is 0.08206. And T is what? 25 degrees plus 273 is 298. Right? Divided by pressure. 1 atmosphere? Yep, 1 atmosphere. Okay. So I got that one in here already. 0.08206 times that and 298 times that divided by 1. So this is 6.79 liters. Rounding error. 6.82. Let me be sure I didn't make a mistake. For number 21, okay. And 06727. Yes, indeed. 2789. 2789. Ah, did I add these correctly? That could be the problem. So 0.0627 and 0.2116 plus. I don't know, 6.627 exponent 2 minus enter and 2.116 plus 779. Okay. So here's a case where my answer is not exactly like the one there, and you don't have the option for none of the above. So you pick the best answer. The closest answer to this one is A. Must be rounding errors, calculation differences, but that's the procedure. Number 23. Right. 23. You're playing with a helium balloon on a typically warm California day. Suddenly the Celsius temperature doubles. Which of the following is true? Well, if the Celsius temperature doubles, does that mean that the volume is also going to double? No, because the Celsius temperature is not the temperature we're concerned with. We're concerned with the Kelvin temperature. So if you have initial temperature is equal to some value x degrees C, and we're saying that the final temperature is equal to twice that, 2 times x degrees C. Right? What does that mean in terms of Kelvin? All right, so this is 273 plus x, and this is 273 plus 2x. All right, what's the ratio of those two? Well, we probably can't calculate exactly what it is, but we can get an idea. 273 plus 2x divided by 273 plus x. If this doubles, right, that doubles, is this going to be doubled? Is that going to be twice? The answer is no. The answer is not going to be doubled. All right, so that the actual temperature is not needed to answer the question. We just have to recognize that the temperature did not double. It increased a little bit. The volume of the balloon will slightly increase. Yes, that's B. Pressure inside the balloon will double? No. Pressure inside the balloon is the same as outside the balloon, so it didn't change. The volume of the balloon won't decrease, and the balloon will not double in volume because we did not double the temperature in Kelvin. So B is the best answer for that one. Let's see, 24. 24. Which of the following statements is true of 19 grams of fluorine gas at standard temperature and pressure? So we have mass of fluorine, 19 grams. Okay? Standard temperature and pressure. Standard temperature for gases is 0 degrees. But if we're going to have a chemical reaction of any kind, it's 25 degrees. So let's just say its temperature is either 0 or 25. One or the other. It may not matter, actually. And pressure is definitely 1 atmosphere. Okay? So, if we're going to draw any conclusions from this, and we're talking about gases, the mass is only a value that can give us the information we need. 19 grams of fluorine equals 1 mole. Right? Just go to the periodic table. Excuse me, no, it's not. It's a half a mole. Let's do it this way. Grams, mole. F2 is 38 grams, right? So that's 0.5 mole. Okay, now let's see. It contains the same number of molecules as a half mole of O2. Yes, it does. As long as they have the same number of molecules, same temperature, same pressure, then N of fluorine equals N of oxygen. That's true. Exists only in the form of ions? No. Occupies a volume of 22.4. What would it have to be 22.4 liters? It would have to be 0 degrees here, 1 atmosphere, and 1 mole. That would give you 22.4 liters. 22.4 liters is the molar volume of a gas at standard temperature and pressure. It contains 6.022 times 10 to the 23rd molecules. Nope. It contains 3.01, just half that many. All right. So A is your best answer. Let's see, how about 28? A compressed gas cylinder at 137 atmospheres and 23 degrees is in a room where a fire occurs. The fire raises the temperature of the gas to 475 degrees. What's the new pressure in the cylinder? Assuming the cylinder doesn't explode, right? So, is this a state function or a before and after? It's a before and after. We've got two temperatures. We've got one pressure. Volume doesn't change. And the number of moles didn't change, right? These factors, pressure, volume, temperature, moles. Pressure, volume didn't change. Moles didn't change. So we're looking at relationship of pressure and temperature. So we don't have a simple law that assigns values to that, but we do have the combined law. P1 V1 over N1 P1 equals P2 V2 over N2 T2. So moles are the same, right? Get rid of that one. And volume is the same. Get rid of that one. Right? So there's our relationship. Let's make this initial, and final, and final. So PI, TI, PF, TF. Initial pressure, 137 atmosphere. Initial temperature, 23 plus 273 equals 296, not degrees, 296 K. Final pressure, that's the question. Final temperature, 475. 475 plus 273 equals, let's see, 7K. All right. So now we just need to solve it for final pressure. So PF equals PI times TF over TI. So plug in the values. 137 times 748 divided by 296. And I get 346 atmospheres. Okay. There's a couple of them are scientific notation, 3.46 times 10 squared atmospheres. And that matches C. All right. Okay, 29. 29. Which of the following statements is true about the kinetic molecular theory? All right. Remember the kinetic molecular theory. The various postulates of the kinetic molecular theory. All right, one is large number of particles. 2, random motion. 3, no interaction. It's like when they hit each other, they just bounce off like billiard balls. 4, point volume. What that means is the volume of the molecule is so small that it's insignificant. Although we do recognize that each of the particles has mass and velocity, right? So each one has, even though it has point volume, the particles do have momentum, right? And we can calculate kinetic energy also. Okay? And interaction with container walls. If we don't have that, then we can't measure the pressure. So which one of these satisfies? Pressure is due to the collision of gas particles with the walls of the container. Here. B says gas particles repel each other but do not attract. Well, according to the theory, they don't do either. C, at least 2 of these statements are correct. Then we have to go to D. The volume of the gas particle is considered to be small. Actually, it's considered to be infinitely small, not just 0.1 mil. 0.1 mil volume would be pretty big for a molecule. So D is false. And E says adding an ideal gas to a closed container will cause an increase in temperature. Well, what's the temperature? Temperature is proportional to the average kinetic energy of all the particles. So if you introduce a gas at the same temperature, it's going to stay the same temperature. You won't increase it at all. Okay, so we found our answer. That was A. Next, 30. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. All right, so we're working from this equation. Magnesium metal plus hydrochloric acid, which is aqueous, yields magnesium chloride in solution plus hydrogen gas. Okay, that's not balanced yet, but we're going to do that. If 3.02 moles of magnesium, let's balance it first. 1 magnesium, 1 magnesium. 2 hydrogens and 2 chlorines. We just put a 2 right there, and we're balanced. Now we go back to the conditions. 3.02 moles of magnesium. And 3.02 moles of hydrochloric acid. Okay. How many liters of hydrogen gas are produced at 1 atmosphere and 49 degrees? So the conditions over here are pressure equals 1 atmosphere and temperature equals 49 degrees C, which is going to be something in Kelvin would be, let's see, 322 K. All right. And the question is, how many liters of hydrogen? What's the volume? It's another one of those ideal gas equations. But we've got to find out how much hydrogen is produced. That's not a gas, that's not a gas, that's not a gas. So all we have to do is find out which one of these is limiting and how much gas did it produce. So 3.02 moles, we need 2 HCl's for every one of these. And that's only one. So this is going to be limiting. Right? And the ratio is 2 to 1. So 3.02 moles of HCl converted to oxygen. We have 2 here and 1 here. So we're going to have, let's see, 1.51 moles of hydrogen gas. Right? 2 into this one. 1, 2, and that's 5. 2. Yep, that's right. Okay, so now all we need is this equation. And we're going to solve it for, let's see, how many liters? All right, we got moles. We're solving it for volume. Right? So moles is 1.51. R is 0.8206. Temperature is 322. And pressure is 1 atmosphere. 1 and 0.08206. 322 divided by 1. So that's 39.9 liters. Okay? Next, and let's skip a few and go down to 34. This one's about out. If temperature and pressure are held constant, the volume and number of moles of gas are. What's their proportionality? All right. The best way to answer this one is if you don't know this is Avogadro's law. Initial over equals, well, it equals a constant. It also equals final over final. Excuse me. So, how are they related? Well, directly proportional. If one goes up, the other has to go up in order to maintain that constant. Direct proportion. Okay, that was simple enough. All right, how about 37? Convert. All right, this is simple. 1.177 atmospheres converted to torr. We want torr. What's the relationship? This one has to be in the denominator. This one in the numerator. So torr is a millimeter of mercury. The relationship for 1 atmosphere is 760 millimeters of mercury, or 760 torr. So this is going to be about 17% higher than 760. 895. There you go. C is the best answer. All right. Let's see. How about 43? A sample of argon gas occupies a certain volume at 15 degrees. At what temperature would the volume of gas be 3 times as big? Pressure remains constant. So we've got argon gas is in our container, and we're going to allow the volume to change, but the pressure is constant. Okay? And we've got argon gas in here. The temperature is going to change and affect the volume. So the initial temperature equals what? 15 degrees. Well, we need to add 273 to that, actually. So let's see, that's 288 K. The final temperature is what? We don't know. At what temperature would the volume be 3 times as big? So we're going to increase the volume 3 times. So VE equals some value. Let's see. Just say V. And then the final volume equals 3 times V. Right? We're increasing the volume 3 times. All right, the relationship is volume over temperature equals final over final. Right? And at what temperature would this relationship be true? Right? So we're looking for the final temperature. And our answers are in degrees Celsius. So we're going to have to convert back to Celsius once we get our answer. Final temperature equals like that and like this. So final volume is 3V, and initial temperature is 288, and the initial volume is V. So these cancel, and we get 3 times 288. A64. That's K. So we need to subtract 273 from it. 195 degrees C. 591 degrees C. Okay? That's 43. Okay. Next. Let's see, 49. Which of the following will give a graph with a straight line and a y-intercept of 0? Okay. It looks like we're comparing volumes and temperatures. Yeah, volumes and temperatures. All right. So if we were to compare volumes and temperatures of just any gas, as the temperature increases, and say this is degrees C, and this is the volume in, say, liters, then this would produce a straight line there, but the y-intercept would not be 0, right? The intercept would not be 0. But if we extend this out here, now this is 0K. Make that bigger. This is 0K. And if we have a volume over here, then we find that the intercept will always be 0 because we changed the scale. 0K here. This is 273 degrees C. 0K. So as long as we're using K as our temperature, the intercept will always be 0. That means the best answer is C. '52. Solid carbon dioxide is placed in a Ziploc bag at a certain temperature. Solid carbon dioxide sublimes, turns directly from a solid to a gas at a rate of 0.726 grams per minute. How many gaseous carbon dioxide molecules are present after 4.84 minutes? This is a dimensional analysis problem. All right? We're starting with solid carbon dioxide, which is going to gas. And we're given a rate of 0.726 grams per minute. All right? And our starting position is 0, and we're going to 4.84 minutes. So after 4.84 minutes, we can calculate how many grams we're going to have left. We're going to produce in the form of gas. So after 1 minute, it's 0.726. That gives us grams. Does that answer the question? No. How many gaseous molecules? So this is grams. We need to convert to moles. Okay? And CO2 is going to be 12.01 plus 32 is 104, 44.01. That gets rid of grams. Now we can convert to molecules. Moles, molecules. 6.022 times 10 to the 23rd. Okay? That's our answer. And I get 3 significant figures. 81 times 10 to the 22nd. Molecules. Okay? I'm at 55. The air in the inner tube of a tire of a racing bike has a pressure of 116.8 psi. Convert this to atmospheres. Okay. 116.8 pounds per square inch. We want to convert that to atmospheres. So what's the relationship here? 1 atmosphere is 14.69 psi. And 4 significant figures. 7.951 atmospheres. Closest one is C. My guess is that instead of this one, 14.7, which would make this one a little bit smaller. Best answer is C. 60? Okay, you're holding two balloons of the same volume. Okay. Balloon here and a balloon here. So volume 1 equals volume 2. One balloon contains 1.05 grams of helium. 1.05 grams of helium gas. The other balloon contains neon. And the question is mass. What's the mass of neon in the balloon? Okay. Well, we can determine how many moles we have here. Assuming the temperature's constant, pressure's constant, we can determine the number of moles here. 1.05 grams of helium converts to 4.00. 1.05, 4 divided. So this is 0.2625 moles of helium. They're the same volume. They have the same number of moles. 0.2625 moles of neon. Now we can convert neon back to grams. We just need the molar mass of neon, which is 20.18. 5.30 grams of neon. Okay, and our closest answer is A. $67. A hydrogen balloon is at 25 degrees, 1 atmosphere, volume of 1 liter. How many grams of argon gas must be added to the hydrogen balloon to achieve a volume of 3.78 liters at constant temperature and pressure? Okay, so temperature and pressure are not going to change. That's constant, and this is constant. All right? So we've got Avogadro's law here. Initial volume, initial moles, final volume, final moles. What are we given? Well, let's see. How many grams of argon gas must be added to the hydrogen balloon to achieve a volume of 3.78? Okay. If we've got, let me see if I can work it this way. Initial volume over initial moles equals final volume over final moles. Do we have an initial volume? 1 liter. Yep. 1 liter. And the final volume is 3.78 liters. Initial moles. We don't know that yet. 67. Hydrogen balloon is 25 degrees and 1 atmosphere and has a volume of 1 liters. So if we have volume of 1 liter and we have hydrogen gas in there at 25 degrees, volume and temperature, 25 degrees C, and 1 atmosphere pressure. Okay. Now we're going to add, we're going to add enough argon gas to increase the volume to 3.78. So we're going from 1 liter to 3.78 liters. So what's the change in volume? Change in volume equals 3.78 minus 1 equals 2.78 liters. And that's argon. Right? We have that much argon. Yeah. We have that much argon gas being added to it. Now we have that many liters equals volume of argon. How about temperature? Temperature is still 25. Plus 273 equals 298 K. And we have the same pressure. Pressure equals 1 atmosphere. So we have volume, temperature, pressure. We can find out the number of moles. That's 1 atmosphere. Volume is 2.78 liters divided by 0.08206. And temperature is 298. So this is the moles of argon. And then we can calculate mass. This is 0.1137 moles. Now we just need to convert to mass, and we need the molar mass of argon. Yeah, argon, 3995. Let's see. And that's 4.54 grams of argon. Okay. All right. Got any more? Yeah, 74. Got a few more minutes. You have a partially filled party balloon with 2 grams of helium gas. You then add 3 grams of hydrogen. Assuming constant temperature and pressure, how many times bigger is the party balloon? Comparing before and after the hydrogen gas has been added. Choose the best formula to use to solve this problem. V equals volume of the gas, N moles of the gas, M the mass. Okay. All right. This is a before and after problem, all right? So the combined gas law would probably be our best starting point. And we're using P1V, okay. The subscript 1 is initial and subscript 2 is final. So we have P1V1 over N1T1 equals P2V2 over N2T2. Okay, what do we have? We have so much helium, we have so much hydrogen, constant temperature and pressure. So the temperature didn't change and the pressure did not change. Right? So we have V1 over N1 equals V2 over N2. How many times bigger is the party balloon? Well, the ratio is going to be V2 to V1. It's got to get bigger. So I'm going to bring this V1 over here and this N2 over here. Right? And see, this is increasing size. This is the final, this is the initial. If we're going to add some to it, then we're going to increase the volume. So V2 over V1 equals N2 over N1. And D seems to be the best answer there. About 78. Which conditions of pressure and temperature are most ideal for a gas? All right, if we go back to the kinetic molecular theory, what we want to do is, for ideal gas, we want to minimize attractions or repulsions. And we want to also minimize encounters, right? The number of impacts we have, we want to minimize that. So that means low pressure, right? If we have low pressure, that means we have smaller numbers of molecules. So we want low pressure. And to minimize attractions, we want to increase the kinetic energy of our molecules so much that when they do impact each other, their kinetic energy is so huge that any interactions are just swamped by the energy of impact. So we want high temperature. Okay? High temperature, low pressure. That would be A. 79. Gaseous compound containing carbon and hydrogen, was analyzed and found to consist of between 80 and 90% carbon by mass. At 145 degrees C in 1 atmosphere, the density of this compound is 2.45 grams per liter. What's the molar mass of the compound? Okay. Well, I'm going to use a little algebra on you, and I know in Chem 100, algebra is not required, but it's the easiest way to solve the problem. And hopefully you'll eventually get to algebra. So what factors do we have here? Let's see. Let me see if that's the best way to approach it. Yeah, I think it is. Okay, so we have, if we include PV equals nRT, that takes into account volume, pressure, temperature, and moles. If we've introduced the concept of density here, so density equals mass per unit volume. Okay? And molar mass, which is what we're after, molecular weight, I call it, molecular weight equals mass per moles, right? Or M over N. Okay. So this is mass and that's mass. This is moles. That's volume, moles, volume, pressure. Okay, so if we're aiming to solve this one, then where would this be included? We would have to solve this one for mass, D times V, and then substitute it right there. All right. So our first substitution gives us D times V over N. All right. If we have a known temperature, a known pressure, constant here, and a known volume, then we can substitute in for number of moles. Okay, so if we solve this one for moles, actually, we could solve it for moles or could solve it for volume and substitute it in here. Let's choose moles. Okay. Moles equals PV over RT. So we're going to have D times V, and then down here, we're going to have PV over RT. Well, you know, in math, if you have a fraction in the denominator, it's the same as flipping the fraction. And this becomes the numerator. So it's D times V times R times T over PV. Okay? I just flip this one, puts this in the numerator, and this one stays in the denominator. So V cancels, and we get DRT over P. Okay, so now we can substitute numbers. The molar mass then is density, 2.45 grams per liter. Are those the right units? Yeah, because this has to be in liters. So this is in liters, that's good. And then our 0.08206 is liter atmosphere per mole K. And then temperature, we need 145, we need 273 plus that. So this is 140, try that again. 145 plus 273. That gives us K. Okay? And then pressure is what? Let's see. Is it 1 atmosphere? Yeah, 1 atmosphere. Okay, let's check our units here. Liters, denominator, liters, numerator, cancels. Atmospheres, numerator, atmospheres, denominator. Denominator, numerator. grams. The only thing left is grams per mole. So we got the right units of measure. Let's see, 2.45.08206 times that, and 145 plus 273 is 418. This is 418K. Times that and divided by 1. So I get 84.0 grams per mole. Okay? Now, there's information in there that we didn't need. 80 to 90% carbon by mass. We didn't need that. Uh, 81. Yeah, we got a few more minutes. Take care of 81. $15-gram sample of a hydrocarbon is placed in a balloon at 1 atmosphere and 25 degrees, and the volume of the balloon is 12.2 liters. The hydrocarbon is 79.89% carbon and 20% hydrogen by mass. Determine the molecular formula of the hydrocarbon. Okay. This is a complex problem that needs to be broken down into pieces. Remember when we were doing chemical formulas before, the empirical formula we can do from the percent composition. That's easy. Then we need the molar mass to convert empirical to molecular, right? So the first thing we can do is take that percent composition and find out what the empirical formula is. Right? So if we say, I'm going to start over here. If we say carbon is 79.89% by mass, percent. And hydrogen is 20.11%. All right. Are we given a mass? 15 grams. Okay. So if it's 15 grams sample, and this is percent, this is grams per 100 grams. So if we use the decimal equivalent, this is 0.7989 times 15 grams. That'll be the mass of carbon. This will be 0.2011 times 15, and that'll be the mass of hydrogen. All right, that'll be our starting point. This is 11.9835 grams of carbon. This is 0.2011 times 15. This is 3.0165 grams of hydrogen. Now we can convert to moles and find the empirical formula. Okay, hydrogen, 1.01 gram per mole. Carbon, 12.01 grams per mole. Right, so this is 1.01 divided into that number, 2.987 moles of hydrogen. And let's see. Yep. 12.01 divide, and this is 0.9978 moles of carbon. All right. This is almost 1. This is almost 3. So the empirical formula is CH3. What we're looking for is the multiplier down here. Right? And to do that, we need to know what is the molar mass of this compound. Okay, if we have 15-gram sample, right, we're looking for the molecular weight or the molar mass. We know what the mass is, 15 grams. The moles, that's what we're looking for, the moles of the gas. And we can do that because we have temperature, right? Temperature equals 25 plus 273 equals 298 K. And we have pressure equals 1 atmosphere, right? How about volume? 12.2 liters. And there's our unknown. So we need our ideal gas equation. PV equals nRT and solve for N. N equals PV over RT. So pressure is 1. Correct? Yes, 1. Volume is 12.2 liters. Gas constant and temperature 298. So we can get the number of moles. 12.2, 0.08206, and 298. Right. So I get 0.499. 0.499 moles. 0.499 divided into 15 is 30.07. 30.07 grams per mole. All right, what's the empirical mass? The empirical mass is 12.01 plus 303 for the hydrogens, 15. So 15 is empirical. That's the actual molecular molar mass. So the factor here is equal to 2. That means C2H6 is our formula. That's it. At least the ones I've marked off. If you have any that are giving you trouble and we didn't cover them, then shoot me an email or office hours.